Hi guys, welcome back. We are still looking at changing parameters of functions. We've looked at a quadratic function and we tried to see what exactly it is about when we are trying to change the parameters. Now, we are going to look at a hyperbolic function, which is a hyperbola, rather, the short way of the actual curve itself. So let's just jump right into it. Right, so remember that a hyperbolic function is a function of the form f of x is equals to a over x plus p plus q, where the p and the q are the asymptotes of this particular function, and the a value is just a constant, right? Remember, we do know what this constant what it does for us, right? It normally tells us things about orientation and about the shape where the parabola is going to, the hyperbola is going to be. So the graph of a hyperbolic function is normally known as a hyperbola, right? Now, if a is greater than 0, the graph normally lies in the first and the third quadrants. Remember, this is my first quadrant, that's my second quadrant, that's my third, and that is my fourth, right? Now, just to explain what this means, if a is positive, because remember that greater than 0 means positive, it simply means that the gradient, although we don't really talk about the gradient with a curve, but the gradient, which is normally change in y over change in x, is a positive one. Why? Because the y values here are positive and the x values here are positive. So either when you multiply them or divide them, you will always get a positive as your answer. Even with the third quadrant, because the y values are negative and the x values are also negative, when you multiply them or divide them, your answer will always be a positive. So that's why the graph will then lie in the first and the third quadrant. But if a is less than 0, which means negative, the graph will then lie in the second quadrant and the fourth quadrant. And the reason is still the same, is the fact that the y values here are positive and the x values there are negative. So multiplying them or dividing them, which has the same effect, will result in a negative answer. Similarly, with the fourth quadrant, I have positive x values, I have negative y values. If you multiply or divide them, it will definitely give you a negative, which has the same effect. Now, someone might ask, why is this important? It is important because just as I give you the equation and I want you to sketch a specific graph for me, you can already have an idea of where it is going to be placed without you finding the table of values first or the intercepts or anything like that. Already you'll have an idea that my two arms need to either be on the first and the third if A is positive, or the second and the fourth if A is negative. So it already gives you a kickstart to say, I know exactly where my graphs is supposed to be. The next step will be then find those values that you are going to plot and join them with a curve. So that's why this is actually important for us to know what the A tells us about where the graph is going to be located. Also, the value of A in that equation also determines the vertical stretch of the branches of the hyperbola. As much as it talks about the orientation of the graph, it also tells us what the vertical stretch is, right? Meaning, the larger the value of A, the further the stretch. In simple terms, the steeper it is, although it's not really a line. Now, to demonstrate this, the first graph, we can say this is 1 over x. And then the second graph, we will then say this is 2 over x. So the value of A is increasing as you're going from left to right with this particular demonstration. And then the third graph will be when I have 3 over x, right? So you can see my value of A was 1, it became 2, and then it became 3. So what this means, as A is increasing, the graph is also becoming more steeper, right? Or it becomes a bit further from the y-axis, which is what the value of A tells us in terms of the shape of the graph. Now, the value of Q, which is the asymptote, this determines the shift of the graph up or down, right? It also represents the asymptote, which is normally represented by a dotted line. Now, what this means is if I have a graph like this or a Cartesian plane, and I say my graph lies there and the other arm lies maybe here, then my asymptote will be lying at that point there, and that's how I'm going to represent that. That is an asymptote, right? Because if I draw a solid line, then there won't be a difference between the Cartesian plane and the asymptote. So we use a dotted line to represent that this is the asymptote. And if you may just remember, the asymptote will be where the graph can approach but never to touch or cross that particular line. And then the value of P will be the very same thing, which is the shift of the graph, but now instead of it being up and down, it actually becomes left or right, and this is also the vertical asymptote of the graph. So maybe it will be at that point there, and it will be represented the same way as the horizontal asymptote, using a dotted line. Now, just to have a specific example of where we see what this is all about, let's consider the graph f of x is equals to 1 over x. First thing I want us to do is to draw the graph. To draw the graph, remember the easier way of doing this is just to figure out what is the table of values, where you have your input values and your output values. Your output values, you get them from the input values, because remember it's independent and dependent variable. Now you can see that x can never be 0 because the equation is 1 over x. So if x is a denominator, definitely this will be undefined. Because a is positive, right, which is 1, already I know it must be in the first and in the third quadrant, right? So already I know something about this graph. And then I can plot my values just as I see them, that minus 2 goes with minus 1 over 2, which is somewhere there. Minus 1 goes with minus 1, which will also be somewhere there, and then you join them with a curve. And then you must show arrows at the end, because these arrows represent that this graph is continuing indefinitely, right? But it will never cross the y-axis or the x-axis. And it simply means that we can say our asymptote here is on the y-axis and it's on the x-axis. The second thing I want us to do is to reflect this graph about the y-axis. And to do that, it simply means the equation was y is equals to 1 over x, right, which is f of x. If I reflect this about the y-axis, the x will become a negative, so it will now be 1 over negative x, which is the same as minus 1 over x. So now the value of a is now a negative, which means second and fourth quadrant, right? So that's where it will now be. It will still be the same graph, but in the different quadrants. Then we need to shift this 2 units left and 1 unit up. To do that, it means from it being at the origin, it will move 2 units left, which will be now at minus 2. So that will be my new asymptote. And then it will also move 1 unit up, which will be at 1, and that will be my new asymptote. And then write down the equation of the new function. Remember, the new function was formed by reflecting f of x about the y-axis, and then by also shifting it 2 units left and 1 unit up. And therefore my equation then becomes x plus 2 and then plus 1 at the end there. Now, just to summarize what we know about this, remember our original equation, right, was f of x is equals to 1 over x. And the graph was on the first quadrant and in the third quadrant. Our asymptotes were the axis of the y-axis and the x-axis, right, of the Cartesian plane. So it was x equal to 0 and y equal to 0. But the graph was now shifted 2 units to the left. So instead of it now becoming x is equals to 0, it moves 2 units to the left, which will land at minus 2. Hence, the new asymptote is now x equals to minus 2. And then the y asymptote was at y is equals to 0. This also shifted 1 unit up. It became y is equals to 1. Now, the domain quickly is x can never be 0, right? Because it cannot cross the x-axis, at the y-axis that is. But now, with the new function, it cannot cross minus 2. And then, although all the other values are existing or the graph is defined on, hence the x is an element of real numbers. And similarly with the range, it's the same thing, but with the new one, it's actually 1 and not 0. And that's how you then analyze and interpret two graphs that you have changed parameters of. All right, guys, that's it for now. I believe that you are still enjoying everything that we are looking at, but I just want us to take a quick ad break just to refresh a bit and look at the work that we've done and reflect a bit so that when you come back, you know maybe what to look for and try to see where you are still lacking some understanding. Please stay tuned. I'll be back just after the ad break.